Welcome to the second video on standing waves, where we're focusing on harmonics. So one thing we learned in the last video is that an opening in a pipe creates an antinode here. But one thing that wasn't explained is that any opening can create an antinode. So when you're talking about a musical instrument, that's why if you take your fingers off of a hole, it creates an antinode, which shortens the wavelength and makes a higher frequency sound. If you ever played the recorder when you were a child, you might have covered up all of the holes, which would have made the longest possible wavelength and the lowest possible pitch sound. I wanted to reiterate the point that any opening creates an antinode. So looking at the different types of standing waves, we have open pipes, closed pipes, and strings with their different areas of antinodes and nodes at each end. In this video, I want to look at these different types of wave which can exist within each, because you'll notice there's this most basic wave up the top, and you can fit more and more half or quarter wavelengths in as you go. So we're going to cover some important names and some calculations of these. So the first name that we need to know is called the fundamental frequency. This is the lowest frequency that can be produced in any standing wave. So it's the top line of all of these three options. In an open pipe, it's a half wavelength with an antinode at each end. In a closed pipe, it's a quarter wavelength, and in a string, it's also a half wavelength. The next word you need to know is naming more complex types of waves. This is called overtones. This is the number frequency higher than the fundamental. So when we jump in an open pipe up from a half wavelength to a whole wavelength, the next most complex option, we call this the first overtone. It's the one resonant frequency slightly higher than the fundamental. If we go too higher, so we go from 1 to 1.5, that becomes the second overtone, and so on. Now, in a closed pipe, the same thing happens in a string. Harmonics gives it a different name again. So while we've got fundamental and we've got each of the overtones, harmonics is a second name for all of these same ones. So harmonic means a multiple of the fundamental frequency. So the fundamental frequency is called the first harmonic because there's one lot of the fundamental frequency. In the first overtone here, this is called the second harmonic because you've got two of the fundamental frequency. This one here is called the third harmonic because there's three of the fundamental frequency, and so on. So I'm going to go through each of these names and each of these examples to make sure we're clear. Remember, there should always be two names for every type of standing wave. So in a string, we start at the fundamental and the first harmonic. Now when we're looking at just harmonics, we then go to the second harmonic, third harmonic, and so on. In overtones, we start the first overtone as the one after the fundamental, so it's always one behind the harmonic. Second overtone, and so on. When we're talking an open pipe, these names are identical, except for the antinodes down here. So again, you have a half wavelength at the fundamental, which is the first harmonic. The first overtone is 1.5, which is the second harmonic. Again, overtones start counting after the fundamental, whereas harmonics you start counting at the fundamental. But a closed pipe is a little bit different. While our overtones are still the same, we've got the fundamental, the next most complex one is the first overtone, second overtone, and so on. The harmonics are slightly different. Because with harmonics, there are multiple of the fundamental frequency. And we start with a quarter wavelength, then go up to 3/4 of a wavelength, which means we go to the third harmonic, 3 times the basic one. The next most complex one, the second overtone, is 5/4 or 1.25 wavelengths. This is 5 times the initial quarter, the fundamental frequency, so it's called the fifth harmonic. So with closed pipes, we go from first to third to fifth to ninth, so we only count harmonics in odd numbers, and this is the exception to the rule. And the next thing we're going to look at is the calculations. There are only 2 types of calculations you can do. The first type of calculations is the V equals F lambda calculations, the formula that you should have learnt last year. The second type of calculation is what we'll cover in a little bit more detail, which is the relationship between the wavelength and the length of the pipe. Because we know how many wavelengths or half or quarter wavelengths fit in each of these standing waves, we can see the relationship between the length of the pipe or string. So I want to cover each of these 9 examples, where if the pipe or string below down here is 40 centimeters long or 0.4 meters long, can we calculate the wavelength of each string and name each of these wavelengths here. So starting off with an open pipe, we have half a wavelength, 0.5 wavelengths, and that's going to equal our 0.4 meters. If we want to calculate the wavelength, we need to divide both sides by a half, which means our full wavelength is 0.8 meters. We could also use logic knowing that if half a wavelength is 0.4, we're going to need to double a half to get to a whole, so we'll need to double 0.4 to get to the whole wavelength as well. Now the two names for this one are the fundamental and the first harmonic. Looking at the second pipe now, we have a whole wavelength equals our 40 centimeters. So that means one wavelength equals 0.4 meters. So again, our answer is just 0.4 meters is the wavelength. When we're talking overtones, this is the first overtone. It's the next most complex thing we can have from the fundamental. When we're talking harmonics, it's 2 times this basic one, 2 lots of this fundamental frequency, so it's the second harmonic here. Finally, we can see here, we've got 1.5 wavelengths in this pipe, so 1.5 wavelengths equals our 0.4 meters. If we divide both sides by 1.5, our wavelength is 0.27 meters. And then again, we have the second overtone, which is the next most complex one, and the third harmonic, because it's 3 times, or 3 lots of these half wavelengths in here. So that's an open pipe. If we look at a string, our numbers are going to be really similar. So again, the half wavelength, we've got half a wavelength is 0.4 meters, therefore a full wavelength is 0.8 meters. We have our fundamental and our first harmonic. But we're mixing it up a little bit now, because now you'll notice that there's 3 half wavelengths here. So this isn't the first overtone, this is the second overtone, or the third harmonic, because it's 3 times this fundamental. So 1.5 wavelengths, or 3 halves, gives us 40 centimeters. So we have to divide both sides by 1.5, giving us a wavelength of 0.27 meters. And this is called our second overtone, or our third harmonic. Finally, you can see that there's 2.5 wavelengths in this 0.4 meters, so it's 2.5 lambda equals 0.4, divide both sides by 2.4, we get 0.16 meters as our wavelength. Now this is the fourth overtone, or the fifth harmonic. It's the fifth harmonic because you're counting how many half wavelengths there are, and the overtone is one below that. Finally, we're looking at a closed pipe. Remember, this is a quarter wavelength, not a half, and that's 0.4 meters. We divide both sides by a quarter, or 0.25, that gives us our wavelength of 1.6 meters. And this is the fundamental and first harmonic. The next most complex one is 3/4 of a wavelength, or 0.75 of wavelength. That equals 0.4 meters. Divide both sides by 0.75 gives us a wavelength of 0.53 meters. And this is our first overtone, because it's the next most complex one, but it's our third harmonic because we've got 3/4 wavelengths in there. Finally, we have 1.25 wavelengths if we count them here, and that equals our 0.4 meters. Dividing both sides by 1.25 gives us our wavelength of 0.32 meters. And this is our fifth harmonic, because we've got 5 quarters in there, but is our second overtone. So these are some examples of how we can use the length of the pipe to calculate the wavelength, and you can do the same going backwards and reiterating our naming here. Some other things you'll need to know is that in an instrument, many of these harmonics or overtones can exist all at the same time. So if you see the red examples here, which are examples for a string, they all overlap, they constructively and destructively interfere with each other to make its final wave. And that final mixed up wave is what you end up hearing as the resultant sound from a musical instrument. So different instruments produce different overtones at different strengths. You know, a closed pipe produces different overtones and frequencies and harmonics to what an open pipe does or a string does. But more than that, they produce these overtones or these harmonics at different strengths, which creates different shaped waves. So we almost always see waves as these nice, beautiful up and down waves. Whereas in reality, they overlap in each other and make these crazy, funny looking waves. They all have the exact same frequency, the same velocity, the same wavelength, but the shape is really funny. So take 2 string instruments, a violin and a piano. These 2 waves produce the exact same note, but the combination of those different harmonics and overtones produce these very different resultant waves. And that's why when a piano and a violin or a guitar all play the same note, they actually sound different to your ear, because the composite or resultant wave is a different shape. So these are the 3 points you can use when you're explaining why when you hear a note from a different instrument, it sounds different to your ear. So here's everything you need to know. You need to know the name fundamental frequency. This is the lowest frequency produced in any standing waves, and these top ones are the example. If you're talking overtones, this is the frequency higher than the fundamental. So this is 1 higher, so it's the first overtone. This is 1 higher again, this first overtone. This is the second overtone because it's the second most complex one that we've got here. And finally, with harmonics, we've got a multiple of the fundamental frequency. So here we've got 3 times the fundamental frequency. Here we have 5 times the quarter wavelength, or 5 times the fundamental, so it's the fifth harmonic. Same with the bottom one round here. A wavelength can also be calculated from the length of the pipe or vice versa, like we saw in all of those examples. And the same note can sound different to you when played by different instruments. And that's because the different overtones are played at different strengths, and there's different numbers of overtones in each instrument as well, making a different resultant wave like we saw here. Alright, now we're going to cover an example. It's the same example of the open pipe getting whirled around. There's 4 small parts to this that we'll cover quickly. So the additional part is that if you swing the pipe slowly around, it produces the first harmonic, or the fundamental frequency. If you swing it faster, it produces the second harmonic, or the first overtone frequency. Faster again is the third, and so on and so on. So Jessica here swings her pipe in such a way that the third harmonic is heard. The frequency of the note is 685 Hz, and the speed of sound in air is 3.4 times 10 to the 2 meters per second, or 340 meters per second. We need to show that the wavelength of the note is 50 centimeters. So this is an example of when you use our basic formula V equals F lambda. We're trying to find the wavelength, so we need to rearrange for wavelength by dividing both sides by the frequency. Then we substitute in what we know for V, it's 340 or 3.4 times 10 to the 2, and what we know for F, which is the 685 Hertz. Finally, that gives us an answer of 0.496 meters or 50 centimeters. In part B, they want us to sketch this standing wave, that's the second overtone or the third harmonic, and label an antinode and a node. So the most basic wave just has 2 antinodes, one at each end, and 1 node in the middle. So we want to go 2 more complex than that. So if we draw the wave here, again we've got our antinodes. It's not drawn perfectly, but you'll get the idea. We have an antinode at each end, an antinode here, and an antinode here. So it's the third most complex wave we can have, and it's 3 times the fundamental frequency. Now when you're actually drawing these in your exams, you only need to draw one of these lines, either the red or the blue, or you can draw both, but you only need one to get the points. And in this case, you'd only need to label 1 antinode and 1 node to get full marks as well. But just to be on the safe side, I've labeled all of them. This third part we're going to look at is calculate the length of the pipe. So we know that the wavelength is 50 centimeters. So we have one wavelength here, one complete up and down of the blue. But we also have another half wavelength. So we know that we have 1.5 wavelengths in our pipe. That's what the length equals. So the length must be 1.5 times our 50 centimeters, or our 0.5 meters. So multiplying that by 2 gives us 75 centimeters, or 0.75 meters is the length of our pipe. The final question is explaining what aspect of a closed pipe makes it impossible to have that same wavelength standing wave as an open pipe of the same length. So the identifying fact, or the key thing, is that a closed pipe must have a node at the closed end rather than an antinode at both ends. So therefore, it only fits an odd number of quarter wavelengths, so 1 quarter, 3 quarters, 5 quarters, which is 1.25. Whereas an open pipe has an antinode at both ends, therefore it fits an even number of quarter wavelengths, or an equal number of half wavelengths, so half, 1, 1.5, and so on. So as long as you explain that there's antinodes at both ends rather than an antinode and a node, therefore it results in different types of waves or different numbers of wavelengths being established, you've answered the question. And this is standing wave harmonics.